Hey everyone, today I've got another little physics problem. First we'll talk about the actual setup, and then how to solve it. So, in this situation, we have a block M1 that starts at rest on a slope of height h. This slope is frictionless. Now, it slams in to M2, and a fully inelastic collision occurs, which means the blocks stick together. Now, they're going to move together to the right until they hit the spring, which compresses with a value of delta C. Now, the first goal of this problem is to determine the expected maximum compression if there is no friction across this distance d, which the two blocks travel together. After that, it turns out that this delta C value is only 1/2 of that expected compression. Therefore, across this distance d, there was energy that was lost due to friction. So the second goal is to determine that work done by friction that is taking energy out of the two blocks. And finally, you are to determine the coefficient of friction of the ground across the length d. So we'll go ahead and just jump in first with goal number 1, to determine that expected maximum compression. And we're going to do this with a bit of the law of conservation of energy and the law of conservation of momentum. Okay, so our energy is coming from our gravitational potential energy, right? Because this block M1 is initially on a hill. So let's go ahead and make a note of that. We know that our initial potential energy is M1GH. Now, after M1 falls this height h, all of that potential energy is being converted into kinetic energy. There's no work due to friction because I said that the slope was frictionless. So, therefore, EI equals EF. So, and we can just write this out in full. U naught plus K naught equals U final plus K final. But we're just dropping the block, it has no initial velocity, and its U final is 0 at the base of the slope. So I'll rewrite this as M1GH equals 1/2 M, and let's give this a term. I'm going to call this V1 because I'm going to be referring to this velocity as the velocity of M1. So we can cancel out our terms, M1, and of course this V1 is squared. So we can cancel out our terms M1, move this 1/2 to the other side, so this becomes 2GH equals V1 squared, but then square root. So the velocity of this block M1 at the base of the hill is square root 2GH. Now, naturally, this is going to collide with block M2, so this entire system is going to slow down a little bit, and we can use the conservation of momentum to figure out the new velocity of the block system. So we can say that P naught equals P final, which are M1 V1 plus M2, and initially M2 is just at rest, so this would be times 0, equals, and I said that this was a fully inelastic collision, so the blocks stick together. So therefore these combine, and they have some combined mass, and I'm going to call that V1, 2, because it includes both blocks of M1 and M2 together. So I'll make this substitution, plugging in root 2GH for V1 equals M1 plus M2 times V1, 2. So this term V1, 2 equals M1 root 2GH over M1 plus M2. Alright, we are getting there now. So that means if these two blocks together have a velocity together, that they're also going to have a kinetic energy associated with them, right? And we can solve for that kinetic energy by doing the following. If we just plug in, we use 1/2 mv1 squared, and this is going to equal the kinetic energy of M1 and M2. So I'll go ahead and think about our substitutions. So this M of the entire system would have to be M1 plus M2, and we substitute in for V1, 2, we put in M1 root 2GH over M1 plus M2 squared. This is times 1/2. Okay. This equals 1/2 times M1 plus M2 times M1 squared. This square is going to get rid of that square root, so then times 2GH over M1 plus M2 squared on the denominator. This cancels out one of those. This 2 and this 1/2 cancel. And so we get that our kinetic energy of these two blocks moving together is M1 squared GH over M1 plus M2. Right? Now, they're going to slam into that spring, which is going to compress until it takes all of that energy away. So we have that our kinetic energy of 1, 2 is going to be converted into U of our spring potential energy. So again, due to the conservation of energy, we'll go ahead and write out this relation. So we have M1 squared GH over M1 plus M2, and the formula for spring potential energy is 1/2 K times delta x, and we called that delta x expected with a little notation, so expected squared. So all we need to do for this is just some very quick moving things around. So we can move that, we can move this k over, we can take a square root. So our delta x expected equals the square root of 2m1 squared gh over k m1 plus m2. Perfect. So that accomplishes goal number 1. Oh my goodness, in my last videos I've been limiting myself to a much smaller page, so this is so nice to have all this room to write stuff out. So I'll go ahead, take this result, and I'll shrink it down. I'm going to move this to the side. And I'm going to put a little 1 here to indicate that we've done goal number 1. Okay. So now goal number 2 is it turns out that the spring only compressed the delta C of 1/2 of that, right? So we have to figure out the frictional work done on the blocks. Okay. So in order to do this, first, let's go ahead and figure out what's the best way to go about this. We can say that the work due to non-conservative forces, being friction, equals the work due to friction, equals whatever that change in energy of this block system is before it hits the spring. Now, that change in energy we can find by taking the difference between the potential energy that we got, right? So I'm going to call this UC minus the potential energy that we expect, which I'm going to call EXP, U expected. So I can solve for both UC and U expected. Again, these are the spring potential energies that first we expect and then that we actually observed. Okay. Let's go ahead and start by just getting what potential energy we observe. So UC, which comes from this delta C over here. So in general, potential energy is 1/2 kx squared. So I'm going to say 1/2 k times delta C squared. And I said that delta C equals 1/2 delta x. So I'll go ahead and make that substitution. Therefore, UC equals 1/2 k times 1/2 delta x squared, which equals 1/8 k times delta delta x squared. And alternatively, if you were to just use the delta x, then you expected equals, it would just be, well, 1/2 k delta x squared. Now, we're going to go ahead and take this difference before we end up substituting back our value for delta x that we got from our first goal. So let's get this difference. This should be negative 3/8 k delta x squared. And we would expect this to be a negative value. Friction is going to be doing negative work, taking energy out of this block system. So I think that's perfectly reasonable. So now we need to make our substitution for delta x expected. And I got a little bit lazy as I started writing out. Technically all of these delta x's should have the delta x expected on it, but that would get very tedious. So I'm going to rewrite out what my delta x actually is, which is square root of 2m1 squared gh over k m1 plus m2. So I'll substitute that in, and we get negative 3/8 times k times the square root of 2m1 squared gh over k times m1 plus m2, all of this squared. Oh boy. It's going to equal negative 3/8 times k times 2m1 squared gh over k times m1 plus m2. These k's are going to cancel out. This 2 is going to multiply on this, make this negative 3/4. So we're going to get negative 3/4 times m1 squared gh over m1 plus m2. And I'll rewrite this as a single fraction. Negative 3 m1 squared gh over 4 times m1 plus m2. And there we go. There is goal number 2 solved. Again, I'm just going to move it to the other side, shrink it, put a little number 2 there, and there we go. So now for goal number 3, we're going to use this knowledge that we now know, which is that our work equals negative 3/4, or negative 3 m1 squared gh over m1 plus m2, 4 m1 plus m2. So this is our work due to friction. Now, what we also know is that work is equal to the dot product of force over a distance, which in this case is FD cosine theta, where theta equals 0 since this block is moving in the same direction. The force of friction is acting in the same direction as the distance that the block is traveling across. So this term is just 1. So F dot D is just FD. So if we were to take FD and set it equal to, and let me make sure that I make this clear, that's the force of friction. And I set that equal to the work done. 3 m1 squared GH over 4 times m1 plus m2. All I need to do is divide by D to get my force of friction. So I'm not even going to bother writing that out in a new line. I'm just going to take that D and insert it. Okay. Now this also equals the force of friction equals the coefficient of friction. So now we're getting pretty darn close to goal number 3 times the normal force. The normal force here is, well, how about we make a quick free body diagram just for good practice. Right, so on these blocks we have m1 plus m2 times g down. So that means that the normal force acting up on them is going to be equal to that. We have m1 plus m2 times g acting up. And then just to complete this, we have our frictional force acting backwards. Okay. So now we just make that substitution for Fn. So I'll say that negative 3 m1 squared gh over 4d times m1 plus m2 equals mu times m1 plus m2 g. So mu then equals negative 3 m1 squared gh over 4 times dg over, or times m1 plus m2 squared, right? We just divided those terms over, right? And I guess in terms of sign, right, whenever we're looking at the coefficient of friction, the actual sign doesn't really matter. You set it to positive, it's just a constant that we use. But that would be its magnitude. So, there we go. We've accomplished all 3 of our goals. I'm so glad to have more space now so that I can do longer problems with more steps. So, that's very nice. Thanks for watching.